Section 2. Contradictory Experiments. Now this is the quandary in which physicists have been in for the last 33 years. Is there any way of discovering absolute motion among the heavenly bodies? We can observe and measure with great accuracy their relative motion. The sun is seen to pass across the sky from east to west, and man at first assumed that the earth was still and the sun went around it. This is the natural and instinctive assumption, for when you first glance out of your Pullman window, you get the impression that the other train is the moving one. But for the last 300 years it has been the fashion to assume the earth was moving and not the sun. That assumption has the advantage of simplifying the calculations of the astronomers, though I never could see why we should have to give up our simple notions of sunrise and sunset to save them a little trouble figuring. The earth moves, if it does move, so quietly and silently that we feel no jar or engine beat to tell us of its motion. If the earth were perpetually shrouded by clouds, could we find out its motion through space or even its rotation? And do we actually get any proof on this point from observation of the heavenly bodies? We see them moving about relatively to each other, and we can represent their movements most easily by supposing that the moon goes around the earth, and that the earth and the rest of the planets go around the sun. But is this whole solar system in motion? So it seems when we compare it with the stars. But who knows if the solar system and all the visible stars are not altogether moving off through space at the rate of a mile or 1,000 miles a second? How can we tell unless we have something that is still and fixed to measure the motion by? It seemed until recently that we had such a fixture, the ether. We know of the sun and stars only from the light that comes from them to us. Light, as we can prove by simple experiments, consists of wave motion. Now, can you have wave motion without something to wave? Sound waves are conveyed by air, but there is no air between the earth and the sun. So as nothing could be found to fill this empty space, scientists had to invent something to satisfy their sense of the fitness of things. The ether was the product of their excogitations. It was a British invention, devised in the Royal Institution, whence have come so many useful theories and discoveries. The ether, as Salisbury said, is simply the nominative of the verb to undulate. It was conceived of as a sort of transparent jelly filling all space, more rigid than any solid, more frictionless than any fluid, more easily penetrated than any gas. It must be more elastic than steel, and yet so rarefied that ordinary matter passes through it without the slightest effort. The ether is supposed to slip between the particles of the rushing earth as the wind blows through the branches of a tree. For many years after its invention, the ether had nothing to do except to carry light about from one place to another. But when the electromagnetic waves of the wireless telegraph were produced, something was needed also to carry them, and this new task was laid upon the shoulders of the uncomplaining ether. When Röntgen discovered the X-rays, whose waves are 10,000 times shorter than the shortest light waves, these were turned over to the ether to run. In fact, it got so that whenever a physicist found any action that he could not explain by ordinary matter, he said, "Let the ether do it." And that hypothetical substance apparently answered every purpose until it came to this question of relative motion. Now, whatever we may think about the ether, it would seem that if there is any such thing filling all empty space, we might use it for measuring the motion of the earth through it, as we did the air current in the car. If the earth is really revolving around the sun, the ether must be whizzing through its pores at the rate of about 19 miles a second. But wait. There is the possibility that the earth carries along with it in its flight through space a sort of atmosphere of ether as it does of air. We must first get rid of this possibility by a preliminary experiment to see if a swiftly moving mass of matter does catch up and carry along with it a little of the ether. This would cause a sort of an eddy or disturbance in the ether in the neighborhood of the moving mass, as a boat disturbs the water. For instance, a ray of light passing close to a rapidly revolving wheel would be a little deflected and show a distorted image. Sir Oliver Lodge tried this experiment and got negative results. That is, moving matter does not disturb or carry with it the ether. Consequently, it would seem, we are left to the only other logical alternative, that the ether drifts through matter, and we should expect to detect this drift by measuring the speed of light in the direction of the earth's motion. It ought to take longer for light to travel from one point to another if the Earth, meantime, is moving away from the first point, and it ought to take less time if the Earth is moving toward it. Well, Michelson and Morley tried this experiment, and also got negative results. It did not make any difference whether the ray of light was sent in the direction of the Earth's movement, or the reverse, or across the line, it traveled invariably at the same speed, 186,000 miles a second. Here, then, were two unquestionable experiments apparently contradicting each other. One proved that the ether did not travel with the Earth, the other proved that the ether did not stand still while the Earth traveled through it. Now, when we get contradictory answers to the questions we put to nature, we must assume, unless nature is nonsensical, that we are asking nonsensical questions. If in the trial of a pickpocket, one witness swears that the thief did not run up the street and another witness that he did not run down the street, the lawyer does not necessarily say that one of them must be a liar. He meditates a moment, and then it occurs to him that possibly the pickpocket did not move, or that perhaps he disappeared into the third dimension by climbing up a fire escape or dropping into a coal hole. So with our ether quandary. If the ether does not move and does not stand still, perhaps there isn't any ether, or perhaps there is a fourth dimension. These are two conceivable ways out of the dilemma, though they are not easy to accept, either of them. If there is no ether, what carries the light waves? If there is a fourth dimension, in what direction does it lie? But it is no harder to believe in or conceive of a fourth dimension than it is the ether, and if the physicist finds that he needs it in his business, he will have to have it. Einstein says he needs a fourth dimension for his formulas. The conundrum of the ages. For 2,400 years, philosophic thought has been concerned with the problem of the relation of space and time. Drop into any of the scientific societies of today, and you will find them discussing whether space is finite or infinite, whether there is any difference between rest and motion, whether length is absolute or relative, whether time and space have real existence, which are the very questions discussed by Pythagoras and Zeno in the Greek cities of Asia Minor. Now, the time spent in these speculations has not been wasted, although it has led to no definite conclusion, for out of it have grown our mathematics and physics. The wandering Jew, who is the only mortal having the privilege of attending the schools of the Eleatics and those of the present day, would observe one difference, that modern scientists try to put their theories to the test of experiment wherever possible, while the ancients were content with thinking them out. Of all the guesses that have been given to this riddle of the universe, none has been more bold and revolutionary than that contained in a paper of 4 or 5 pages, contributed in 1905 to the Annalen der Physik by Albert Einstein. The controversy it precipitated has not altogether been confined to the realm of pure reason, for scientists are but human, and as such are not entirely uninfluenced by patriotic prejudice. In this brief paper he proposed a new theory of the universe based upon 2 postulates. The first was the principle of relativity, that all motion is relative. This means, for instance, that we would never know the motion of a smoothly moving train if the windows were darkened, and that we could never discover the forward movement of the earth if we could not see the heavenly bodies. Einstein's second postulate was that the velocity of light is independent of the motion of the source. This is a hard one for our reason to swallow, for it means that nothing can travel faster than light, 186,000 miles a second, and that you cannot make light travel faster than that by giving it a swift send-off. It is the same as saying that if a man standing on the cowcatcher of an engine threw a ball forward, it would not make any difference with the velocity of the ball whether the train was running at full speed forward or backward or standing still. But the experiments of the American physicists, Michelson and Morley, who measured the speed of light and found it the same whether the earth was moving toward the source of the ray or away from it or at right angles to its direction, confirm Einstein's second assumption. If we accept Einstein's 2 primary postulates and his later principle of equivalence, his theory clears up this ether drift difficulty, as well as various other riddles of the universe. It explains the shifting of the orbit of Mercury that Newton's theory could never account for. It foretold the deflection of light by the sun's gravitation that the observations on the eclipse of last May confirmed. A third test, the shifting of the lines of the solar spectrum toward the red end in a gravitational field, has not been met. Such technical points concern only physicists and astronomers, but Einstein's relativity theory, which 2 out of the 3 experiments support, carries with it certain speculations as to time and space that are upsetting to current conceptions. End of section 2.